Hey everyone, welcome to this explainer. Have you ever wondered what actually physically happens inside a massive AI model? Today, we're going to take a micro to macro journey into one of the most fascinating engineering achievements in recent AI history, which is the V3 era DeepSeek architecture. We're going to trace the exact physical and mathematical pathways that make large-scale generative AI possible, moving from the journey of a single piece of data all the way up to the massive GPU clusters that power the whole thing.
Okay, let's dive into this. Think of this agenda as our operations manifest. We've got 1. The next word generation. 2. Inside a DeepSeekMoE layer. 3. Dispatching to the experts. 4. The training feedback loop. 5. When routing fails. And finally, 6. The great dispatch problem. We are literally going to trace a single data packet straight through the system.
All right, kicking things off with section 1, the next word generation and the origin of the token. So, let's ground this technical discussion in something you probably do every day. You sit at your keyboard, you type a chat prompt like, explain quantum physics, and you hit enter. The model now has one singular job, generate the very next word. But to really get how it does this so efficiently, I want you to imagine shrinking yourself down to the size of a single token, just a tiny digital fragment of your prompt, entering this massive system. You are about to experience a highly coordinated series of physical handoffs. Before we go any further, we really need to clear up a common misconception. When we talk about a mixture of experts, or MoE, an expert is strictly a mathematical feed-forward subnetwork. It's just a chunk of parameters within a specific layer. It is absolutely not a specialized human department, it's not a mini LLM sitting in a virtual room waiting for a question, and no one explicitly tells the expert what to specialize in. It's simply a highly optimized neural network pathway. Moving on to section 2. Inside a DeepSeekMoE layer. And just a quick note, we are currently looking strictly at inference operations. Let's look closely at what actually happens when the model is generating an answer for you. This is the mechanical sequence of our token's journey through a single layer. Step 1. The attention mechanism produces a contextual hidden state for our token. Because it has this context, it moves right to step 2. A router network scores the available experts based on how well they match the token. Now, because the router scores the experts, step 3 triggers. A top K selection makes a hard, constrained decision, picking only the highest scoring experts. And finally, step 4. The token's activations are physically dispatched over to the specific GPUs that host those selected experts. And this right here brilliantly illustrates the extreme sparsity of the DeepSeek model. Out of 256 possible routed experts sitting in a single V3 era layer, our token only activates 8 of them. That is the real magic of the mixture of experts. Instead of lighting up every single parameter in a gigantic monolithic block, which is incredibly computationally expensive, we only activate a tiny fraction of fine-grained experts. This saves a massive amount of computational cost and memory bandwidth. But our token's journey in this layer isn't just about those 8 routed experts. DeepSeek uses a really clever dual approach. While those 8 selected routed experts are conditionally active and doing their specialized math for peripheral knowledge, they actually recombine with an always-on shared pathway. This shared pathway is constantly active processing common knowledge like basic English grammar. Once the specialized math and the shared math recombine, the token hops back onto the residual stream to repeat this entire cycle in the next layer. All right, section 3, dispatching to the experts. Let's disambiguate the routing math. Now, what's really interesting about this slide is how we untangle the math that stops this whole system from falling apart. Basically, how does it pick those 8 experts reliably? We have to untangle these 3 highly confused routing metrics. First up, the router score. This is used during inference, and it simply measures the token-to-expert affinity, how well the data matches the math. But then, we have selection bias, which operates during training. This is a load-balancing adjustment to make sure experts are utilized fairly. Finally, we have the output weight, which brings us back to inference. Once the experts finish their compute, this is the final multiplier used when combining their outputs back together. Understanding this separation between inference affinity and training bias is absolutely crucial. Which brings us to section 4, the training feedback loop. Now we're zooming out to look at training operations. Okay, let's zoom out from our single token's micro journey and look at the macro-level control systems governing the entire physical GPU rack during training. DeepSeek v3 pioneered something called auxiliary loss-free balancing. Historically, MoE models used an auxiliary loss function to literally force the router to spread tokens evenly, But that often conflicted with the model's main objective of minimizing training loss. Basically, it made the model worse at its actual job just to keep the experts busy. DeepSeek fixed this by adding a bias term called gamma directly to the affinity scores. This brilliantly balances the expert loads without degrading the model's core performance.
Here is exactly how that training loop works in practice. Step 1. The system constantly monitors recent expert loads across the entire physical cluster. Step 2. It adjusts that bias term, gamma. If an expert is overloaded, its bias is decreased. If it's starving for tokens, its bias is increased. Step 3. This actively influences future top K routing choices. So the system is dynamically self-correcting to ensure no expert starves and absolutely no expert is overwhelmed.
Section 5. When routing fails. Let's look at system boundaries and bottlenecks.
We've got to be real here for a second. Selective computation is inherently dangerous. When you rely on dynamic routing, things can break down. And if the dispatch system fails, you hit these severe bottlenecks. You can get routing collapse, where one single expert gets all the tokens and the system just grinds to a halt. You can get undertrained, dying experts that the router completely ignores. You face massive GPU capacity pressure. And crucially, you face expert parallelism communication bottlenecks. Remember, expert parallelism means we are physically moving massive amounts of token data across network cables between different GPUs to reach the right experts. If that traffic jams, the whole model pauses. But to solve those communication bottlenecks, DeepSeek released DeepEP, which is a highly tailored communication library. And this is a wild piece of engineering. To get extreme performance on Hopper architecture GPUs, they actually discovered and utilized an undocumented PTX instruction called ld.global.nc. It's technically undefined behavior for non-coherent read-only memory, but they stress-tested it to guarantee correctness. It's a hardcore fix that allows them to bypass traditional communication bottlenecks entirely. Finally, Section 6, the Great Dispatch Problem, the cost of selective computation. Let's bring the micro and macro systems back together to summarize these architectural trade-offs. It's really important to explicitly anchor this explainer in time. Everything we just traced, the 256 fine-grained experts, the auxiliary loss-free balancing, the multi-head latent attention, this is the specific causal journey of the V3 era mechanisms. As you might know, the April 24, 2026 release of DeepSeek V4 introduced entirely new architectural paradigms. So we're not claiming every current model operates exactly like this, but rather we're mapping the brilliant engineering foundation of the V3 architecture.
And that leaves us with our final takeaway, the core truth of scaling modern AI. When you move away from activating every parameter and you choose to run sparse, efficient networks, you don't actually eliminate computation, you transform it. Selective computation creates a massive dispatch problem that has to be meticulously balanced, physically communicated across GPUs, and constantly checked for wrong routes. The intelligence of the model isn't just in the parameters anymore, it's in the logistics. So as models scale even further, we really have to ask, will future breakthroughs come from better math or simply from better traffic control?